All right, we're going to talk about some basic applications of L'Hopital's rule. L'Hopital is really a way of taking the limit of some weird functions, some functions that end up, or expressions that end up in the indeterminate form. So that means when you go to evaluate the limit, you get something like 0 over 0 or infinity over infinity, and obviously you cannot evaluate that. When you get this situation, it's called indeterminate, and you can use L'Hopital's rule to evaluate the expressions. And L'Hopital's rule is simply, it's pretty nice actually. So let's say you have some expression f of x and some expression g of x, and you get that indeterminate form. What you can do is you can actually take the derivative of the top and the derivative of the bottom. No quotient or anything like that, just derivative of the top, derivative of the bottom, and that will equal your limit. And it's actually, I should fix this. It's actually that it equals the limit as x approaches c of f prime of x over g prime of x. And then you could just reevaluate the limit of the derivative over the derivative. So I'll show you some examples how that works. Like I said, you may want to cross this out and fix this because it technically is the limit of the derivative, because this is sometimes it's something you have to do a few times. So I'll show you how it works. Let's go on to the next page. Okay, here's a real simple one. And this is one that we learned. We already know the answer to this. It's 1, right? This is one of the ones that we just learned, and now we're going to use L'Hopital's to kind of prove it. So if you were to go ahead and evaluate this, you'd end up with the sine of 0 is 0, and then if you just plug in a 0, you get 0 over 0. So this is indeterminate. So let's go ahead and do the derivative. So the limit as x approaches 0, the derivative of sine x is cosine x, and the derivative of x is just 1. Well, now you can evaluate this limit pretty easily. If you plug in a 0 here, you get the cosine of 0 over 1, and the cosine of 0 is obviously 1, so this whole thing is 1 over 1, which is 1, and that's why we can always just take this expression here and say it equals 1. It's one of our rules that we learned at the beginning of the school year. Alright, so let's do another one here real quick, a real quick, easy example. This is also one that we learned a while ago. If we just try to plug in the limit, we end up with 1 minus, the cosine of 0, again, is 1, over 0. So we would get 1 minus 1 is 0. We'd get 0 over 0. So there's the indeterminate form. So that's our check. We have to check that first to make sure L'Hopital's applies. Unless they tell you to use L'Hopital's, you don't have to do the check. But this is what you have to do to check and make sure you can actually use L'Hopital's. Now let's go ahead and do the derivative. Well, the derivative of 1 is 0. Derivative of negative cosine is positive sine. And the derivative of x is 1. Now when you go to actually evaluate this, you end up with basically just the sine of 0 over 1, and the sine of 0 is 0, so you get 0 over 1, which is, of course, 0. So all I did is take the derivative of the top, take the derivative of the bottom, and then reevaluate that limit. It's pretty straightforward, pretty easy to do. Let's do some a little bit hairier ones here. Okay, let's check and make sure that L'Hopital's applies first. We're just going to plug in a 0 here. I'm going to do that in blue. If I plugged in a 0, I'd get 2 times 0 minus the sine of 0 all over 0. Well, 2 times 0 is 0, and the sine of 0 is 0, so we end up with 0 over 0. Yes, L'Hopital's can be applied. That's an indeterminate form. So let's go ahead and take the derivative. We're going to keep the limit notation there, right? And just take the derivative of the top and the bottom, no quotient rule. So the derivative of 2x is just 2, and the derivative of negative sine x is negative cosine x. And derivative of x is just 1. Now we can evaluate this new limit, and we would get 2 minus the cosine of 0 all over 1. And we know that the cosine of 0 is 1, so we get 2 minus 1 over 1, which is just 1 over 1, which is just 1. So you can see this is a really handy tool for evaluating tricky limits like this. Let's do number B, or letter B, sorry. So let's check it first. Okay, so let's plug it in. If we plug in a 0, we would get the square root of 4 plus 0 minus 2 over 2 times 0. 4 plus 0 is just 4, and the square root of 4 is 2, so 2 minus 2 over 0. Of course, this is 0 over 0. Good. We can use L'Hopital's. So let's go ahead and do that. We're going to have to do the derivative of this. And you may want to rewrite this top part as 4 plus x to the 1/2, just to kind of make your life a little bit easier. And let's go ahead and do it. So the limit as x approaches 0. And what would be the derivative of this? Well, let's just kind of do like a little mini chain rule. Let's pretend like this was like our u real quick. We would just move the 1/2 out in front. So I'd have 1/2 4 plus x to the negative 1/2. And then I would have to multiply by the derivative of the inside, but the derivative of x is just 1, so I don't really have to put that there. And the derivative of negative 2 is 0, so it's minus 0. And on the bottom, the derivative of 2x is just 2. Okay, we could try and clean this up a little bit. It would look like the limit as x approaches 0 of 1 over 2 times the square root of 4 plus x. And then that's divided by 2, which is the same thing as multiplying by 1/2. So I'm just going to write it like that. Let's go ahead and evaluate this new limit. I would have a 1 on top. I'm going to go ahead and multiply these two 2's together. That would be 4 square root 4 plus 0. So that's 1 over 4. The square root of 4 is 2. So this is 4 times 2. And this whole thing ends up being 1/8. That is a fun problem. Okay. So, pretty interesting. We were able to take a pretty complex limit problem, use L'Hopital's, and it's pretty simple. Let's go to the next page. Okay. So, remember that we always have to check and see what we get if we just evaluate the limit. And this is actually a limit that approaches infinity, right? So remember we had some rules with that. And the rules were that we just look at the coefficients. So this one, we don't have to use L'Hopital's. We could just see that right away it's going to be 5 over 3 because they have the same degree. These things don't matter when you go to infinity. The constants don't matter. And so this would just be 5 over 3. But to show you that it works even using L'Hopital's, we could do L'Hopital's and think about what's the derivative of 5x minus 8. Well, this is just 5 and this is 0, so this would just be 5. And what's the derivative of 3x plus 1? Well, 3 plus 0, so this would just be 3. And the limit of a constant is just simply that constant. And so there we go, 5/3. Pretty cool. All right. Let's do secant x over 1 plus secant x. Let's first evaluate it. What happens if you plug in a pi halves? So you would have, think about secant as 1 over cosine of pi halves over 1 plus 1 over cosine of pi halves. This is a little bit of a weird one because if you kind of think about this, what you really have is you have 1 over 0 divided by 1 plus 1 over 0. And it's not technically one of our two indeterminate forms, but it works because what this is really is another indeterminate, because really if you think about this, you could kind of say that this approaches infinity if you think about the big little principle. So really this is similar. I would just say it's kind of similar to saying like infinity over infinity. And so yeah, we can use L'Hopital's because this is definitely indeterminate. This is a weird situation that we can't evaluate normally. So let's go ahead and do the derivative. I'm going to move all this stuff out of the way. So the derivative of secant x is secant tangent x. So I'm just going to write secant x, tangent x on top. Derivative of 1 is just 0, and again, the derivative of secant x is secant x, tangent x. Well, we can see that now we have the exact same thing on top and bottom, so this just ends up being the limit as x approaches pi halves of 1. Well, again, the limit of a constant is just that constant, so the answer here is just 1. All right. Almost done here. Got some fun things going on. Last two problems. You've had some experience with L'Hopital's now. I'd encourage you at this point to pause it and try these two on your own. See if you can evaluate them. They're a little tricky, but I think you can do it. So go ahead and pause the video now and then come back when you're ready to check your work. Okay, so the first thing I did for practice A here, example 4A here, is that I just checked to see that you do get a 0 over 0 when you plug in a 0. So that's indeterminate. So we take the derivative of the top, that's secant squared theta. Derivative of the bottom, that would just be 1. And this really, if you're dividing by 1, it's really just secant squared. And secant squared is really just 1 over cosine squared. So we're really just asking about the limit as theta approaches 0 of 1 over cosine squared. So now we can evaluate. Let's plug in a 0. 1 over cosine squared of 0. Well, cosine of 0 is just 1, and 1 squared is 1. So this whole thing is just 1 over 1 over 1. Pretty easy. Let's go to the next one here. The trick to this guy is for you to recognize that it's not in a ratio. Remember, in order to use L'Hopital's, you have to have a ratio. So what we do first is we use this negative exponent, or if it was positive, we could make it negative and put it on the bottom using our exponent properties. Now when I plug in, I would get some infinity over another infinity. Well, that's indeterminate. So let's take the derivative. Derivative of x is 1. Derivative of e to the 2x is e to the 2x times 2, because there's a little chain rule. And now I can plug this in, because now when I plug this in, I get a constant over something to an infinite power. Well, this is really, really big, and this is really, really small. So this is the big little principle. So when you have something, some constant over infinity, remember that equals 0. That's one of our rules of limits. And so this whole thing is 0. That's it for L'Hopital's. At least basic L'Hopital's. There's another video that goes into some more advanced applications. See you guys next time.